Um, so it's our topic for today is quite complicated. It's about multi-view projection. Um, this is partly related to the course on descriptive geometry. In fact, some of the lessons I'm giving you is exactly the same. But it's a good thing for you to either recall or to get yourself acquainted with it, because normally students taking up descriptive geometry usually have difficulty understanding the subject. So then I don't know when you're supposed to take the descriptive geometry, whether it is this semester or next semester. So multi-view projection is simply representing 3D objects in 2D media, okay? Because the real object, any object that you can see, for example, your computer is an object, it is three-dimensional. But then if you're going to translate it to drawing, to paper, so you have to know how to do it in 2 dimension, okay? And then the 2 dimensional drawing, there's so many types. Of course, you can make a perspective, an isometric, an orthographic. For today's lesson, we are going to focus on the orthographic. Okay, we're going to talk about basically uh, two variables: the line of sight and the plane of projection. So, what is the line of sight? So, because we'll keep on talking about this all throughout. Imagine yourself looking at your monitor, and then try to imagine a point there where you're focusing on the monitor, and then a line made by that point and your eye is called the line of sight. Okay, so the monitor is now the plane of projection. So anything that you see, if the monitor is a glass, anything that you see through the glass is actually like projected to the glass. That's why you see it. So that's why it's called the plane of projection. And then there are two methods of projecting reality. One is to parallel, which is more of unrealistic, because in the real world, everything you see actually converge at the point. So the perspective is the more realistic way of drawing or projecting points of an object, to form an image. But in this class today, in this course, in this particular topic, we are going to deal with parallel. We're going to analyze how parallel projection is done. So these are basically the difference between parallel projection and perspective projection in terms of illustration. Okay, so in perspective, all the projection line converge towards a single point, which is your eye. But in the parallel projection, everything is like projected parallel to the plane of projection. Multi-view projection is an orthographic projection for which the object is behind the projection plane and the object is oriented such that only two of its dimensions are shown. Okay, so that's why it's three-dimensional, because there is the width, there is the length, and then there is the height. There are 3 dimensions. But when you project the object to a plane of projection, we will only see two of the dimensions. Okay, so it's either the height or the length only, the height of the width, or the width and the height. There are 3 views of objects drawn when we make multi-view drawings. So in each view is a 2D flat image. The views are defined according to the position of the plane of projection with respect to the view or to the object. So later on, we will see what we call a glass box, where we put the object inside and then project the object to to the sides of the box. No? But I should have placed that slide earlier. But anyway, we are now familiar with the front view. We have been hearing that maybe even before you took up architecture, some of you. So the front view is basically the view of the front. So I later define what the front means. Okay, so there's also the top view, and then the difference between the front view and the top view is the top view is always seen from the top, from above. Okay, it is always horizontal. Okay, always horizontal. So let's if you're a bird looking down, so all you see are the top view. Now in AutoCAD, if you're familiar with, if you've tried AutoCAD at all, the drawing, the default drawing you see is actually a top view. Okay, and then so that's why when you make plans, so it's like that, no? And when you make, when you know already how to make the work workspace into 3D, maybe in isometric, you'll see that your drawing is actually lying down. And then we have the side view or the profile view. Now, in other countries, in some countries, they call it profile instead of side view. Okay, so if you're reading books from other countries, you might be confused, no, when they mention profile. Profile, what is this? So it's actually just similar to the front to the side view. So let's go back. So in the front view, you have the height and the width. In the top view, you have the depth and the width. And then on the side view, you have the depth and the height. Okay. So these are the three principal views that we normally use in our drawings. Um, and this, it says here, always position the top view above and aligned with the front view. Okay, so it should be aligned. If I draw a line from one edge here going down, it should align with its corresponding edge in the front view. And then the front view and the right side view should also be aligned. No? And then we normally take the right side view because we can also have a left side view. But in engineering drawings, at least where three views, a minimum of, actually with two views, you can already picture or imagine the 3D object. But the three views are standard. No? It gives you the complete data for the 3D object. Let's tackle principal views. Now, this is the glass box that I mentioned earlier. So imagine that this box is made of glass and inside is your object. So maybe you have a sort of a gear, not a gear, but a machine part here. And then you project towards the surfaces of the glass box. The way you project is by parallel projection, which means that it is you project perpendicularly to a parallel plane, to a plane parallel to the surface. No? So there you generate your front view, you generate your top view, and you generate your right side view. But the box has 6 sides, so you actually generate also a view at the back here, which is the back view, and also a corresponding view on the left side, and then there should also be a view at the bottom. Okay, so there are 6 principal views in the end. Now, to view it, you should face the plane. For example, to view the front view, you should be on this position. To view the right side view, you should go to the side and then view the plane perpendicularly to the line of sight. And then if you want to view the top, then you should what? You should fly or you should go to this position and then look at the plane here. the horizontal plane perpendicular to your line of sight. Okay, so that's the idea. So I'm not asking you to fly, you know. And then if you unfold the box, like what we're trying to do here, or represent here, we get now a flat image of all the views. So it's like this one, you unfold everything, so you get the flat image. So now you have the front, the bottom, the top, the right, left, and also the rear. Okay, and so if you fold them up again together, and then you paste the edges here, you go back to your box. So what is the standard view used in engineering and technology? I mentioned that there are three: the top view, the front view, and then the right side view. Okay, but later on we will also talk about another standard which is applicable or which is adopted by European countries. So it's not international. No? It's not everyone in the world uses this. Some other countries use a different standard. But in the Philippines and in our class particularly, we will use this. So if you give me the other type, so that's wrong. No? Even if that type is acceptable in a European country. We're not a European country, by the way. So methods of transferring measurements, you can do it by using scale or your divider. In case some of you don't know what a divider is, it's like a compass, but the 2 points are made of needles. A compass has a needle and a lead, a pencil lead, but a divider has two needles. Okay, or a miter line, which is basically your 45-degree triangle, and then you project to that, and then murag banda, no? So you project to the other side. So project vertically, and then where it hits the 45-degree line, it projects horizontally towards your drawing. Now, this divider and miter lines are ways of drawing without the use of a ruler. Okay, so in principle, all of this geometric construction method of drawing was made to do away with the ruler. Okay, so that you can actually construct even if you don't need to keep on measuring because it will take longer. So as long as you construct it this way, you project it this way, so you can be assured that the measurements here is transferred exactly there in another view. Okay, so that's the main purpose for all of these exercises. Um, there is also what we call first and third angle of projection, and this is where I mentioned to you the other standard for representing the three views, three principal views: the top view, the front view, and the side view, right side view. So imagine your glass box divided into four parts. So we now have four quadrants. Okay. Um, so the first angle projection, we imagine it to be the object placed in the first quadrant in our illustration here. Okay, and then the third angle projection is where we imagine that the object is placed inside the third quadrant. Okay, it says here that third angle projection is used in the US, Canada, and many other countries throughout the world. A first angle projection is used mainly in European and Asian countries. I may have, well, anyway. So what happens is like this. So we focus on the first quadrant and the third quadrant with the object inside. And then we separate the two boxes, the two quadrant box, and then put them side by side. So this is now our first quadrant box. the third quadrant box, and then we project the way we projected earlier, and then we come up, we unfold the boxes, so we come up with this drawing. Let's backtrack a bit. Third angle, European, okay, Asian. So this is what we what I presented earlier is the normal or the usual way of presenting the three views: top view, front view, and right side view. And I mentioned that this is also what we use in the Philippines, because this is what is used in US and Canada, as mentioned earlier. And then the other side, the top view is at the bottom, and then the right side view is at the left, is the way that Europeans and some Asians, because we are also Asians, no? So some Asians, especially those colonized by the European countries, like Vietnam is colonized um, by France, or Hong Kong is colonized by Britain before. So therefore, they follow the European standards. But Philippines was colonized by US, by America, so we follow American standards. So this is another way of presenting. So if you come across a book that presents the drawing this way, so probably the author or the book was published in a European country. So don't be surprised and don't criticize saying that they don't know anything. Um, they still follow their own standard. So how to draw it? So very simple. First, decide on the front view. Now, in a house, the front view is very obvious. So it's the one facing the street or the one facing the approach. Or if it's not very obvious, it should probably be the one with the main door. Okay. So having established the front view, so all the other sides are followed, no? The side view and the rear view. And then draw construction lines to the going to the right. Notice that the construction lines are thin and do not touch the front view. These lines will line up the side view. So these are construction lines. But earlier, when we were trying to make lines from the object towards the planes of projection, we call them projection lines. And so we draw the right side view this time. And then notice the gap between the views. It's referring to this between the two objects. By the way, the object here is the 3D object you see at the upper right. Now this one, which we call the front view, and then the right side view, are called images. So they are images of the objects. Okay, so they're not the object. And then we project towards the top, and then we also draw the top basing on the dimensions here. Notice that the gap is the same. So this gap between the front view and the side view has the same distance with this gap with the front view and the top view. Okay. So if I were to put a 45-degree line here at this corner going that way, and I project this up and then project towards here, they should align. Okay, that's the idea. This one should align with this one with a 45-degree line. So it is unusual for you to draw the top view here and then your right side view very far away. Okay, or the other way around, your right side view very near and your top view very far away. Okay, so that's not, at least in engineering practice, engineering drawing, that's not acceptable. But we are architects. We draw a house and we do not represent it this way because we end up drawing most of the time one drawing in a piece of paper. As much as possible, we want to maximize the piece of paper. like, okay, the plan, the roof plan in one paper, the elevation in another paper. But you might end up, when you make, for example, smaller drawings like details, so that's where you cross the line, no? You go into the realm of the engineering drawings. These are mechanical gears, probably these are blocks, but this could be a detail of something. Um, and then you're going to present it to the engineers, so they have to understand it in their own language. And so we put there the dimensions and also indicate the hidden lines. Okay, by now, I don't know, maybe you should be able to interpret where the hidden line should be. You know? For example, these lines here are hidden by this surface, therefore it comes out hidden line. Also, this one here cannot be seen from the because of the surface, therefore there's a hidden line here. Um, let's try to define some terms for edges and planes, related to edges and planes. Okay. So where a surface intersects with another surface, you form an edge, and that's an edge line. Now there are three types of edge lines. One is the normal, and then the inclined, and the third is the oblique. Okay. A normal line is you have to understand it in a different sense than the usual normal. It's not the normal and abnormal line. Normal in engineering parlance is means that it is perpendicular to the line of sight. Okay, so I'm looking at something, and that something is perpendicular to my line of sight. That something is normal to my line of sight. Okay, so um, but normal lines, um, strictly speaking, normal lines, inclined line is also part of normal line because they are perpendicular. But normal lines should also be parallel to the other planes of projection. Okay. In some other books, they would classify this as normal line and oblique line only. So normal line, you have either the horizontal line or the vertical lines. Okay, and then if they angle, they're called inclined lines. So therefore, under normal line, you have three types: horizontal, vertical, and then inclined. But here it's they differ it, so you can understand it in any way you want. Doesn't matter. But the oblique line is very unique because it is not parallel to any plane of projection. Like for example, in this illustration, line 1, 2, it's not parallel to the front plane. It's not parallel to profile. It's not even parallel to the horizontal plane. Therefore, the line is called oblique. What does that tell us? When a line is parallel to a plane of projection, it is shown in true length, meaning to say you can measure it from the drawing, and that is exactly the length of the actual object. In this case, in the front view, line 3, 4 is parallel to the front view, therefore it is normal to the front view. Then it is shown in true length. You can measure this line, and that's the actual measurement. But in the other views, like this one, in the top view, it is not parallel. It is angled to the top view. Therefore, it's the same line, but if you can see, they have the different measurements. So this is called the foreshortened length. Okay. This one also, in the side view or the profile plane, on the profile view, 3, 4 is not parallel to the profile plane. Therefore, it is not in true length. It is foreshortened. Okay. Now, in an oblique line, since it is not parallel to any of the planes, therefore it is not seen in true length in any of the drawings. Okay. And then if the question arises on what is the true length of line 1, 2, that's where we introduce another plane of projection, the auxiliary plane, which is our last topic later. No? So before we go to auxiliary plane, let me introduce also the types of planes. So you also have the principal planes, the front, horizontal, and the profile plane. Then just like lines, you have normal lines, you have principal planes. Then you have inclined lines, you also have inclined planes. So they are perpendicular to one plane of projection and inclined to another, to an adjacent plane of projection. So the same, no? Imagine the box, the glass box earlier, but the one side we try to um, move it at an angle, but it is still perpendicular to the front view, so it's an inclined. But an oblique plane is not parallel to any of the principal planes of projection. So, like this drawing, the A is perpendicular, is parallel to the front plane, and then B is parallel to the top plane, and then C is parallel to the right side. Okay. Now D, it is actually at an angle to the top plane and the profile plane, but it is perpendicular to the front plane. Okay, so that is called an inclined plane. But E is not parallel, not even perpendicular to any of the principal planes. Therefore, we call it an oblique plane. Okay. Now, what does that mean? There are terms here that I placed and I also mentioned earlier. True length, true size, or true shape, and foreshortened length, foreshortened size, foreshortened shape. Okay. So if the shape or the surface is parallel to your plane of projection, it is shown in the true size. Meaning to say, for example, in this leftmost drawing, so you can measure all of these edges, and they're the actual measurements of the object. You can measure this angle, and that's a true angle. Okay. Um, but in this case, this surface, this triangular surface, is not parallel to the plane of projection, in which case, this case, the front view. Therefore, you cannot um, you cannot measure. Okay, uh, except for the lines. For example, this line here, this edge is parallel to the front plane, so you can measure this is this true length. This one, since it's at an angle, so it's not true length. Okay, and this one also, since it is angled, this is also the same line, so they're not true length, they're foreshortened length. And the whole surface does not show the true shape. Now, this is very useful when you are trying to analyze roofing, especially if you're not using flat roofs. And in the Philippines, we're not supposed to be using a lot of flat roofs because we are in a tropical country and we're just actually inviting problems when we make use of flat roofs. Okay, um, it will be prone to leaking. Okay, although the only advantage of flat roofs, especially for students, is that you don't need to think about all of these things. You don't even need to use a triangle. You just need you just draw vertical and horizontal lines. In other words, these are uh, designs for the lazy architects. Okay. Um, so But don't worry, I think this will also be reviewed in your descriptive um, geometry class, unless you already reviewed it. Therefore, you already tackled it. Therefore, we're actually the ones reviewing. Since we are at the topic of edges and planes, so some edges are hidden, which I mentioned earlier, but some objects have hidden um, hidden surfaces, but they are curved. Okay, and we're referring to some holes. The holes you have to know how to represent in a drawing. If it's a true hole, a hole that goes all the way to an object, so it's basically this way with a center line at the middle. Okay. Now, a blind hole does not go all the way through. Okay, so in this drawing, it ends with a 30-degree taper, the tip, but it can also be flat as long as it does not go all the way. Therefore, you have to draw how it would look like inside. Okay, this one is a counterbore hole. Sometimes when you put bolts, you want the top of the head of the bolt to be flush to the surface. Therefore, you have to make a hole which is enough to accommodate the head of the bolt. Okay, so therefore it's like this, no? They have a bigger diameter hole and a smaller diameter hole for the shank of the bolt. Now, if if the allowance for the head is angled, so we call that countersunk, not counterbored. Okay, because it may not be a bolt, it may be a screw. Okay, with the screw head, you want it flush to the surface, so you create a hole. In this case, it's tapered, and then before the smaller hole, which is for the shank. Um, this spot face is actually for the same like counter bore, except that it is very thin. And then threaded is like your screw, um, the threading, you show it this way. Okay, the inner and outer diameter of the thread is shown. So you do not show each thread. So it's understandable already. And so if you encounter edges which are curved, so how do you draw them? So it's like this. So if it's a corner, then it's curved. You do not show the line where it starts to curve because in principle it's tangent, it's smooth. Okay, so it ends up like a rectangle only on the top and also on the side, but you see its true shape in the front view. Now, if it is this way, of course, this is an edge and that's also an edge. So you show that. Here, this is a corner, therefore there is a line here. Okay, but this one again is a smooth curve, therefore you do not show. On the other side, this is obvious. But if the plane here is perpendicular to the plane here, meaning to say this is like a principal plane, so you put what we call a limiting element. So you project that, you put a line. Okay, this one is angled, so it is like smooth. But once it does this, especially if it goes in, therefore you're already going to make the limiting element here, which defines an edge, and then also the limiting element which is hidden. Okay, so this is quite tricky. And so some other ways of showing the intersection. No? This is curved, but then this is plane, so there's an intersection. but this is tangent, so when it's drawn, there's no line. Again, when it's tangent here, there's no line, and same here, there's no line. Even in the, uh, there should be two lines here, no? There should also be a hidden line here if this were uh, a corner. But since it's not, it's tangent, so there's no line. So let's go finally to auxiliary views. Now this is very confusing, so please bear with me and try to focus. An auxiliary view is an orthographic view taken in such a manner that the line of sight are not parallel to the principal projection planes, the front, the horizontal, and profile plane. There are an infinite number of possible auxiliary views of any given object. So in principal planes, you're limited to what we just defined, to the sides of the box, the glass box. But you can have an infinite number of auxiliary planes. In other words, an auxiliary view is an orthographic view which is projected onto any plane other than the front or frontal, horizontal, or profile plane. An auxiliary view is not one of the six principal views. So we have been repeating that, no? There are times when one of the six principal views will not completely describe an object. So if your design is like what they call pabali-bali, no? It's a lot of angles. So at one point you need to measure, to show the measurement of an angled wall, which is not parallel to either the front or the side. So therefore you have to make another view where that angled wall is actually facing you so that you can put all the dimensions. So that's the use of the auxiliary view. Okay. So this is especially true when there are inclined or oblique planes or features on an object. For these cases, special orthographic view called an auxiliary view can be created. Okay. So this is what we mean. Although in this drawing, okay, so um, here we can get this edge, the dimension of this edge, because it's in true length. Okay, but then if we wanted to know more about the surface, we cannot do it here or the other on the top or on the right side because they're inclined. So whatever is the design there or the drawings there are not shown in their true measurements. Therefore, we have to make this face us. So therefore, it's like we adjust also. So we fly and then we look at a angle at so that our line of sight is parallel to the perpendicular to the surface, and then we're able to draw the true shape and the true size of that surface ABCD. So that's basically the principle. Okay, so um, we can have as many, and then we can even do multiple auxiliary views. We make one auxiliary view and then after that make another. So that becomes a secondary auxiliary view and then make another auxiliary view based on the secondary auxiliary view and we have a tertiary. So it becomes very complicated. But in your descriptive geometry, you might end up with the secondary auxiliary view for the sake of getting a true length. Okay, because you have to keep on rotating the object in your drawing. So good luck to that. No? Okay, so this is how it would look like. These drawings at the left is your top and front view, and then this uh, this T here means plane T for top view. This number one is your auxiliary plane number one. So you project to that, and then you've got this drawing, and then you have another auxiliary plane number two, and then you project to that again, and then you have another drawing, and then um, you have auxiliary plane number three, project to that, and then you have a third tertiary auxiliary view, so third drawing. In this case, I don't know the problem why they have to make these three views. But in some cases, for example, I just wanted to get the true shape of this part of the roof. especially if I'm going to put some designs there. So I have to make an auxiliary view which is parallel to the roof surface. Okay. Fold line method is the object is suspended in a glass box to show the six principal views. We actually used this earlier, created by projecting the objects onto the plane of the box. The box is then unfolded. Okay, so we already discussed this. But then what happens in an auxiliary view is like this. So we introduce another plane which is parallel to the surface, so that when we look at it, it's projected now perpendicularly to the plane, so we get the uh, true shape. Okay, and then if we draw it, so it's something like this. And notice that the measurements of the plane from this folding line is the same. Okay, that's the principle. So we mentioned earlier that we cannot have a drawing where the top view is near the front view, but the right side is very far away. So their distance towards where your imaginary uh, like barrier, no, or boundary between two planes should be equal. So how do you draw? How do you draw this? Um, Okay, decide to draw the angled face of the block using the front view because an edge view is available. So this is the edge view of the plane. So we project perpendicularly, and then we make auxiliary plane represented by this. So this is now the folding line, similar to this and this one for the top view and then the side view. And then we transfer the distances of the object towards the front view here in our new auxiliary plane. And then once we transferred, we are able to draw the object now. So in this drawing, this surface, which is angled in the front view, is now shown in its true surface or true shape. But then now the rest of the plane, which is here and here, are now foreshortened. So they're not true shape because we're actually just looking for this one. Um, so second auxiliary view, we already mentioned that. Now I wanted to focus on partial auxiliary view. Read that later. In partial auxiliary view, what we actually wanted is, when I mentioned that we're interested in this one, it's also possible to just draw this and not to draw the rest. Okay, so in partial auxiliary view, if you draw everything, so this is what we get. But it's also valid for us to draw only the surface interesting where which is of interest to us. Okay, so we are interested in this plane here with the hole. Okay, so therefore we draw only this. So that's partial auxiliary view. Ah, okay, curvatures. So to draw the curves, you need to put points because we cannot transfer anything. So therefore, you have to, like the drawing in step 4, you have to divide that into certain segments so that you can have points, and then those points are the ones that you're going to transfer and then plot so that you get your true shape. Okay, so it's like our exercise. So with your French curve, just join the points together and then try to create a smooth curve, and then that's your true shape. So summary, let's just read through this. Auxiliary views are a type of orthographic projection used to determine the true size and shape of inclined and oblique surfaces of objects. Normally, auxiliary views are projected from existing principal views. However, auxiliary views can also be drawn first and then used to create a principal view. This is done when a true measurement can only be obtained by an auxiliary view, and that measurement is needed in order to create a principal view. So this technique is called reverse construction. We did not tackle that, but the principles are the same. So any number of auxiliary views of an object can be created. Successive auxiliary views can be created by projecting from an existing auxiliary view. Okay, that's it, no? So I'm going to post later today, not immediately, because I still have to transfer. Um, we're not going to work on auxiliary views. Okay, so I'm simply either reviewing or just introducing it to you for your descriptive geometry. And also to make sure that I mention that as reference in case we encounter problems requiring auxiliary views. Because after, I think our next topic, after our next topic, okay, next week we won't meet because that's the USC days, and we are told that we should not have a synchronous uh, class, so no online class. Then the following week, when we come back, we will be making architectural drawings already, floor plans, elevation, sections, and then we might encounter oblique surfaces like in your roofs and some walls. Okay, so I'm going to post this and I will ask you to just draw the top view, front view, and side view of this figure. If you notice, this is a grid. It's like an isometric grid. So each grid is actually 1 unit, or it can be 1 cm, 1 centimeter. Okay, so that's simply your assignment for this week. I'm giving you until Saturday to work on it, so there's no rush. No. Basically, that's it. So, any questions? So, Google Meet has this new feature of blurring the background, so and I'm enjoying it. Okay, so if there's no question, just so I'm going to dismiss this class, and I'm also going to please wait for the assignment to be published. It will be anytime today, probably after lunch. So that's it. Okay.